Lesson 10 review, I suppose we'll call it, of last time. So recall, in this class, we have many products. We should actually list them. If I say x times y, no vector hats, no extra information, we might say that this is what we call the scalar product. And let's think about the scalar product using the where did you come from, where did you go map. What's the input on the left and the right hand side of a scalar product? Left is a scalar, right is a scalar, output is a scalar. Same exact dot is used. Here we have a times x. Could you guess what that one is? That's called a scalar vector product. Let's go ahead and think about that particular map. What's on the left, what's on the right? Scalar on the left, vector on the right, vector gets produced. And to be completely honest, we should probably be a little bit careful and say that this is actually what we call a scalar column vector, which says that really not only do we have a scalar column vector, if we call this thing n by 1, but we might actually just expand that to, perhaps we call this 1 by n. And in this case, we would call that what? Scalar row vector. And I think it's worth recognizing that those are not the same thing. The actual arithmetic that underlies this is very, very similar. We're just bringing the scalar inside and doing a bunch of scalar multiplications. The reason that these aren't the same, however, what size is the right argument in this product? These dimensions do not agree. They're not the same operation. What's the output size? 1 by n. Same idea. The output, the right argument on these have different dimensions. The output have different dimensions. These are different operations. We can call both of them scalar vector multiplication because on the left there's a scalar and on the right there's a vector. Formally speaking, we're not doing anything crazy, but I do think it's important to identify that distinction because as we go on through the course and we're thinking about the different operations, the stuff that we put into those operations very much matters. And that's one of the trainings that we're doing when we identify dimensions is we're figuring that subtle set of differences out. Next one that we might talk about is if I take x times y, and if I say that x is an n by 1 and y is an n by 1, what did we call this thing? Inner product. And I might actually say in Rn. Let's go ahead and look at that inner product. Where did we come from? Where did we go? N cross Rn into R. We could also define, we have not done this in this class, and I don't always think that this is necessary. We could have defined, instead of an inner product in terms of columns, we could have defined an inner product in terms of rows. We haven't done that, but it is quite possible to do that. This thing, instead of being an inner product in the space of columns, what would it be? Yeah, inner product in R1 by n, in which case if we were looking at the where did you come from, where did you go map, what are the inputs on the left and right hand side of that multiplication sign? Row vector on one side, row vector on the other side, and scalar valued output. Next we had something called outer product. And an outer product, what did we have on the left? What did we have on the right? Depends on what size you want to say. We've generally been thinking about matrices as having mango rows and November columns, or M rows and N columns. And in that situation, we might say that the column vector on the left has dimensions m by 1, and the row vector on the right has dimensions 1 by n. This is what we're going to call the outer product. And in this case, let's look at that dot. Remember that the thing on the left is called the left argument, and the thing on the right is called the right argument. And what we're asking is, what is the size of the thing on the left? This would be an m by 1 column vector. What's the thing on the size of the thing on the right? 1 by n. What type of output does it have? M by n matrix. We also had something that was quite famous, which was that's called the scalar matrix multiplication. What's the scalar matrix multiplication problem? What's on the left-hand side of that dot and the right-hand side of that dot? Scalar on the left, matrix on the right, and the output would be in m by n. Out of all of these operations, which is this analogous to? Yeah, you can kind of group them together, right? These two kind of are grouped together. This one is in a world of its own for now, at least. This one kind of groups together with this one. This one kind of groups together with this one, right? I guess all of these together kind of form the same concept as a scalar in one thing. There were some people on the first exam that used a really, what I would call, less than accurate approach to describing scalar vector multiplication. I had some people tell me that if I wanted to create the force vector, that I would write that as m times 9.8. I was relatively generous, and I didn't mark the whole problem as 0, right? Because I understood what they meant. But formally speaking, do we have such an operation where you have a matrix on the left so far, before lesson 10, a matrix on the left and a scalar on the right? No. And it does matter. This is a class in which the products that we study are non-commutative. And we'll talk about that as we get further into the development of matrix vector multiplication and matrix multiplication. And this is the type of thing, when I'm asking you to identify the dimensions of every matrix and every vector that you put on, I'm literally asking you to get hints in the type of operations that we're doing. Last time that we spent together, we developed new operations. Do you remember what those were? Yeah, we did develop transformations, but we developed new products. Do you remember what the first one was? Something that looked like this? Yeah, you might call that a matrix column vector product. Let's do the analysis of where did we come from, where did we go. What was the size of the thing on the left? R m by n. What was the size of the thing on the right? R n by 1. What was the size of the output? M by 1. In this case, we took in a matrix, in a column vector, and then we put out a column vector. We had this terminology where we were thinking about the arguments. We had what we called the left argument, and we had what we called the right argument. And one of them we thought of as passive, and one of them we thought of as active. The passive thing is the thing that we're hitting. The active thing is the thing that we're using to change the thing that is actively passive. Or you could call them factors. Anytime you have a product, usually you think about the things that you're multiplying as the factors of that product. So in this case we have two factors, the left factor and the right factor. Do you remember which we talked about as passive in this paradigm?
In this case, the left.
Left one. And the reason that that was passive had to do with the statement of the matrix vector multiplication problem. Which one was given in the matrix vector multiplication problem? Let me think about it this way. When you think about matrix vector multiplication, what's the function? What's the input? The vector is the thing that we put in. The matrix defines the function. It's called the matrix vector multiplication function, right? From that standpoint, when we're hitting x, we are kind of using x to run through the function, right? So we're thinking about the a as being passive, and the x is the active element in that sense. What did we say in matrix multiplication when the left-hand matrix was the passive matrix? What did we do? Cut it up into columns, and then we said that in order to form this product, we're going to take linear combinations of the columns of A with scalar coefficients coming from the rows of X. And the fast way to say that here is that the inner dimensions must agree. For every column, there should be one scalar, one row, right? So that was one form of matrix vector multiplication. What was the second form that we talked about? Vector matrix multiplication. And in this case, we said that why don't we look at that as a vector on the left-hand side, and we'll keep our matrix of the same dimension to have a theme running through. In this situation, what size was y? You could say y transpose if you want. What size was the vector on the left-hand side of that product? 1 by m. In which case we might call this a row vector matrix multiplication. Let's go ahead and analyze the dimensions of the left and the right-hand side. If we look at this dot as a product, what size was on the left? A row vector of size 1 by m. What size was on the right? A matrix of size m by n. What output vector was produced? What was the size of the output vector that comes out of this product? 1 by n. And then again, in this situation, we're thinking about, as a way to prime the pump in the discussion of matrix multiplication, in algebra, we usually think about manipulating algebraic expressions using addition and multiplication if it's linear algebra, right? If it's quadratic algebra, we might use square roots. If it's absolute value algebra, we might use absolute values, blah, blah, blah. But in that case, one of these things is going to be the thing that we start with, and the other is going to be the thing that we're doing to it. In my mind, when we're looking at matrices, I want you to think about that as the stuff that we start with, and then these are the inputs. So you could run through a bunch of different inputs, but the matrix doesn't change. From that standpoint, we would think about which as passive in this paradigm, the left or the right? The right. The claim that I'm trying to have us make specific connections between is, if we think about the passive element on the left, we chop that matrix into columns. On the other hand, if we think about the passive element on the right, we chop that thing into rows. This matrix vector multiplication, we take a linear combination of the columns. This matrix vector multiplication, we take a linear combination of the rows. The last thing that we saw from all of this analysis was this implies that we can actually do a map between what we might call the inner product between two vectors. In this case, we had x1, x2, all the way down to xn, multiplied by y1, y2, all the way down to yn. What is that inner product? x1, y1 plus x2, y2, all the way down to the n, which we called xn, yn. My claim is we can now think about that as a product in either of these flavors. The one that comes out most easily, in my feeling, is this one. Could you give me a matrix here and a vector here that produces that result. And the way that I would think about this is, let's think about these as individual rows of a matrix. So now we're thinking about the individual scalars. They're the least interesting rows that exist because there's only one coefficient in each of those rows. What's the whole idea of vector matrix multiplication? Take a linear combination of the rows with scalar entries defined by the individual columns. Here are the rows. If we look at that matrix, here's the matrix, 1, 2, all the way down to yn. So this is now an n by 1, kind of an interesting way to think about it. N by 1. What's the corresponding row vector? x1, x2, all the way down to xn, and that becomes a 1 by n, in which case now we have two different products used to express the same underlying concept, right? This product over here, which one is it? It's the inner product. Why is it the inner product? Yeah, the dimension on the left-hand side is equal to the dimension on the right-hand side. They're both column vectors. This product over here, it really depends on which paradigm you're in. My claim is you can actually interpret it as either of these products. If you interpret it as this product, if you interpret it as the matrix vector product, what's the matrix, what's the vector? The matrix would be X transpose, the right-hand side vector would be Y. On the other hand, if you think about that as row vector matrix multiplication, what's the matrix in that case? Y. What's the vector? X transpose.